Hey, what's going on YouTube? What's up? So, I think that today is day 10 of our brand new math stream, and today's going to be fun. I woke up early this morning. I apparently couldn't sleep super well, so I came a little bit prepared today. So, today I do have a title and a topic in mind. And yeah, this morning I was putting together some notes and just thinking, like, where do I want to go next? What do I want to show next from what I remember as a TA for linear algebra like 15 years ago? I loved the linear algebra way back in the day, and I remember learning about Markov chains a long time ago, just briefly, and I thought that it could be a cool topic for today. So we've got the prisoner's dilemma. We have Markov chains and Pascal's wager. And then we're going to work a couple of problems from Strang. So, first thing of all of these streams, if there are any comments or questions from prior videos, I'll just take a moment to answer all of those, or any ones that I find interesting. But we don't have any of those because we're a brand new stream. So that's fine. Now, I wanted to just briefly give like a little bit of flavor and thought about why, because I don't want to be disingenuous about what I'm doing here. So before I forget to say it, I'm available as a tutor. I could be your private tutor. I could be your kid's private tutor. And yeah, I love teaching. I just really love math and I really love teaching. So hit me up. I made a brand new email. The math hobbyist, the math, whatever, you can spell it. And it's probably in the video description or something. The math hobbyist at gmail.com. So that's kind of the primary reason. Secondly, I am building some iOS apps, and I have a couple of little toy side project types of apps that I want to show off and be able to get some eyeballs on and show over time, especially in these streams. And I don't like social media at all, but some really smart people I've talked to say, you need it. Sorry, get over it. It's necessary if you want to build a business today. So here I am. That's fun. There's always part of me that's wondering about grad school. I really considered it during the pandemic lockdowns. I really, really considered it, but then I decided not to. Math is hard. And yeah, I don't know. Math is hard. That's what I've learned. Someday we will do grad school, I think, just for fun. Warm fuzzies. Really, I should have said number one, fun. My name is the Math Hobbyist, and it is true. I want to rebuild math as a hobby, something that's fun for me, that I enjoy doing just in and of itself. And if I can share it with others, why not? I also have fun talking to the camera and hanging out with like-minded people, meeting like-minded people. So hopefully this can just be a fun channel, I think. Warm fuzzies. Like I feel like I can just get some warm fuzzies from teaching some people some cool math that most people haven't seen. I enjoy it. I like to try to be able to explain any concept to anybody to some level of degree. And I don't know if that's accurate. I'm going to try to explain some hard shit here in this channel, in this video, in this stream. And it makes me feel nice and warm and fuzzy inside if I can help some other people enjoy math a little bit more, or be good at math a little bit more than they were. Yeah, I don't know if real altruism exists, but at least I feel warm fuzzies. And then finally, Skynet, right? Like, if I ever decide to go back to work in tech, Skynet is hiring, and linear algebra is very useful, and very much in hot demand right now if you want to help build Skynet. So it seems like a skill that's really worth revisiting and relearning. Maybe I want to go work on Skynet, or I could tutor. All right, so today we're going to be talking about Markov chains. And in the process, I said review, but really I'm going to briefly introduce probability. Most people have seen this, some people haven't, so I want to at least show like a tiny bit about what probability is. And then we've got some other motivating examples that are fun, like I want to talk about Pascal's wager for a second. This is a great example of a 2x2 matrix. And then we can talk about ChatGPT for a second. We're going to solve a couple of problems from Strang. Those should be in the video title as well. And then finally, in the last part of this video, I do want to follow up because I totally bombed the last stream. I wrote down the formal definitions of vector spaces according to Strang, according to Exler, and I haven't checked, but I bet Shilov is pretty similar, just like a little bit more terse, but similar. And then according to Lang. So this time I actually wrote it down, and we'll be showing the formal definition, the same concept, according to 3 different people. Which I hope gives some flavor, even if you don't understand what the hell I'm talking about by this point of the video. I hope it can impart the idea that there's not one true math, that math can be seen from different angles. Like, these 3 people disagree. They just straight up disagree on what a vector space is. And so if you only ever take one course in linear algebra, just know that there might be more. There might be more. All right, so let's get started. I want to introduce first thing that we need to do is introduce matrix multiplication. So the way that you multiply 2 matrices together is by multiplying the row of one to the column of the next one. So here I'm going to take the ith row of the first matrix and the jth column. So maybe the first row and the second column. And then that's going to calculate the number in that spot in the new matrix. So in this case, here I have I equals 1. Whoops, not I equals 6. What are we talking about? I equals 1 here. J equals 2. And we're going to calculate this number C12. Remember, I is first, the row is the first number, and then the column is the second one. So we're going to calculate C12. Well, what the hell is that? What we do is you take each element and multiply like the first number from the first row multiplied by the first number in the column. And so we multiply those together, 1 times 6, and then we add the multiplication of the second number and of each, 2 times 8. And then what is 6 plus 16? That is 22. So I wrote that right here. 22 is 1 times 6 plus 2 times 8, same thing. And then if you do that for each of these, then you get this matrix at the bottom of the screen. For example, 15 and 28 equals 43. That 43 is the bottom left number there. And what I was doing was multiplying 3, 4, and 5, 7. So you can double check that for yourself if you need to. Probability. So here's the next topic. Most people don't know this, but not everybody. And if today's your first day, you are one of the lucky 10,000. That's an XKCD thing. there's way more than 10,000 people learning about probability per day. But anyways, let's continue. Probability. Let's take the clear example that a lot of people know of. What are the chances of flipping a coin heads 3 times in a row? If you take a coin and you flip it, it's a 50-50 chance that you get heads, right? Now, well, if we want to look at it geometrically, this is a cool way to think of it. We can live in this little quantum world. Quantum world. Where we haven't flipped a coin yet. We have one coin and we flip it. And then we're going to create 2 separate parallel universes. One universe, it lands tails, and in one universe, it lands heads. So if we do live in the universe where it lands heads, then if we decide to flip it again, we're going to create 2 more parallel universes. In one of them, it lands tails, and in the other one, it lands heads. So maybe it does land heads, and we're in that parallel universe. Then it can either land tails or it can land heads. If it does land heads, then we now live in this universe. Okay? What we can do is we can count how many universes did we just create by flipping a coin 3 times. We created 8 separate parallel universes. And it turns out we landed in this one, which is really lovely. We keep winning. We keep winning and getting heads again and again. So there are 8 in total, and there's only one of those universes where we got 3 heads in a row. So that's like a way to really see it and imagine, be able to count each one. But then algebraically, you can think of this as flipping 1 heads. There's a 50% chance of that. You can also write 50% as 0.5 or 1/2. So I'm going to use the 2 interchangeably, or the 3 interchangeably throughout this entire video. So 3 heads, the chance of getting 2 things, 2 independent events is a technical term, to happen in a row, is multiplying their probabilities together. So getting 3 heads in a row is getting heads and getting heads and getting heads, which is 0.5 times 0.5 times 0.5, which is right there. And then that turns out to be 1/8. Again, like, this is 1/8 is 2 to the 3rd. And we got 8, exactly like we did when we drew it out. Because in the real world, you're not going to be able to draw probability problems because there's just way too many parallel universes to keep track of, right? So we can ask ChatGPT, and it turns out that is 12.5%. Cool. So, any questions? Anybody in the chat? Nobody's in the chat. All right, let's keep going. All right. I think that this is fun to mention. In my first video that I made, I was talking about math that I like to show kids. And I like to teach kids, like even like 2nd graders, like people learning addition for the first time. I really like to show this triangle because people like triangles. People like shapes and geometry. And it's kind of a game. I mean, you just teach somebody like, hey, if you ever want to practice addition, practice is good. Practice makes perfect. If you ever feel like you want to practice some more problems, you don't need to wait until a worksheet. You can just grab a pencil and start making this triangle. It's going to start getting harder at some point. at some point for anybody, it's going to start getting harder. The numbers are going to become 3-digit numbers or become 4-digit numbers. Maybe you remember, maybe you've memorized one of these, so you can just take a shortcut right there and start from that row. Anyways, go watch that video. I think it was fun. That's number theory 1. I also introduce my story just a little bit, my backstory and stuff. And while we're at it, let me just show a couple fun things I always show. There are cool patterns in this. Because, of course, there are infinitely many rows. We're going to get all of the numbers in that second diagonal. And then this one is really cool because 3 is 1 plus 2, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, 15 plus 6 is 21. And then I bet that the next one is going to be 21 plus 7. And hey, that is exactly what we got. And we see it here. 10 plus 5, 15 plus 6, 21 plus 7. That's a cool pattern. So it's more magical if you just focus on going this direction. It's less magical if you look at the number to the right of it. But anyways, it's a fun little thing to show people, including kids. All right, so Pascal's wager. This is a cool topic, I think, to introduce the example of a 2x2 matrix. And I wrote this early this morning, and I feel it's like a little bit half-baked, but let's try to do it. So Pascal, speaking of like flipping coins, he was studying something like slightly different, but we could reframe it as like, should I bother trying to flip 100 heads in a row? Like, is it worth it? Like, the chances are low. The chances are super low. But is it worth it? Is it worth trying to flip 100 heads? Well, that would be, based on what I just talked about a second ago, 1/2 times 1/2 times 1/2 100 times. There's a very small chance. Like, this is like, what's that book? Rosenstein and whatever. Rosencrantz and Guildenstein are dead or something. There's a book that's really great, and they keep flipping heads. It's funny. But it's 0.000 with 31 zeros in a row, 79. That's about 0%. So it's very, very small. But if you flip 100 heads in a row, you will get infinite happiness. You will get infinite happiness if you flip 100 heads in a row. That's tempting, right? But if you don't flip, if you try and you fail, you wasted a little bit of time. But you're not too disappointed. You're not going to be bummed out that you didn't flip 100 heads in a row, because that's what you expected. You expected that that's not going to work out. So the chances of the downside is small, but the upside is huge. So I don't know. Should you try to flip 100 heads in a row with that coin? Maybe. Let's denote the idea of playing this game as IG, also known as possibly wasting your time. So IG is wasting time. So over here in this 2x2, here are the options. You've got infinite happiness in the top left, and you have, like, if you choose to play and you win, then you get infinite happiness. If you choose to play and you don't win, you're a tiny bit bummed out. You procrastinated and you're just a tiny bit bummed out. Not a big deal. If you don't choose to play, but somebody told you that you would have won that game, if somehow magically you knew that you would have won that game, you're going to be infinitely sad, because you're going to live the rest of your life knowing that you could have bragged about flipping 100 flipping a coin the same 100 times in a row, I would be infinitely sad about that. Anyways, if you decide not to play, and you know that you wouldn't have, if you know for sure that you wouldn't have, so what? That's what you expected. So you're just like a tiny bit happy. Okay? Cool. So let's continue. The prisoner's dilemma is kind of similar. And the reason I'm bringing up both of these is that these are both kind of like the introduction of game theory. I think that's accurate to say. I don't know anything about game theory other than this. This is kind of my the extent of my knowledge of game theory. I love board games. There's Dominion in the background for me, but and I know that there's a lot of really neat math behind game theory that I'd love to learn and practice and work on with you all. And hopefully there's somebody out there who's a game theorist who can help teach us some math. So the prisoner's dilemma is kind of similar. I like to use, whenever it's people, we've got two prisoners, Alice and Bob. Okay, so they're both in prison, and I forget the exact story. I wish I looked it up right before this. I was almost fully prepared. But they're both prisoners, and they are trying to escape, I think, together. If they both decide to cooperate, how does this work? Why does this work this way? If they both decide, so they're both trying to escape the prison together, I think. Alice and Bob are trying to escape the prison together, but based on the fact that two people are leaving at the same time, I think that increases the chances that they can get caught. And then if they get caught, then they're going to have to spend 1 extra year in prison. Because the responsibility was split between both. Or it's like if both of them cooperate, they probably both, it doesn't matter. If they both cooperate, they're both in some way going, the expected outcome is that they're both going to probably get caught and probably both spend another year in prison together. But if Alice, if Alice rats on Bob and pins all the blame on Bob, then Bob is going to have to spend 3 more years in prison. And Alice is going to escape. Alice is going to be able to escape fully free. Alice gets infinite happiness by defecting, by ratting on Bob. And Bob is out a little bit, 3 extra years in prison. So what we're doing here is we're analyzing the probabilities or the options. You can either choose to cooperate or you can choose to defect. Likewise, Bob's choices, Bob can defect and Bob has no loyalty to Alice, and so Bob can escape and get infinite happiness, and Alice is 3 units sad. But if they both defect, then they both spend 2 more years. I don't really remember the exact formulation of this. Let's move on. Over here, we can think of a lot of these things. This is going to be a sloppy stream sometimes, y'all, and that's okay. A Markov matrix. Back to matrices in linear algebra. Markov matrices are one of the most, I think, useful uses of linear algebra. and it is basically matrix multiplication. So 1/2, 1/3 here, and 1/2, 1/2. This is just some random matrix that I found. If you multiply that row and that column, then this number here turns out to be 5/12, which is just a little bit less than half. So it's less than half, but more than a third. Yeah, so that's just matrix multiplication in the second line, but what makes something a Markov matrix, I think it's the only requirement, I could be wrong. I think it needs to be square. A square matrix means that it has the same number of rows as the number of columns. And each column needs to add to 100%. So 50 and 50%, 33% and 66%, they're both 100% unless you're a nerd. So as long as every column adds to 100%, that's like every possibility is written down in this matrix, like all of the different probability options are written down, then you have a Markov matrix. All right. And so, for example, here, what a Markov matrix does is in this row, or in this element, it says, back to flipping coins, if you flip a coin, if the last flip that you had was heads, then, so maybe I'm saying 1 is heads and 2 is tails. If you flip a coin, you start with a coin with the head side up and you flip it. If it's a perfectly balanced coin, if it's perfectly balanced, then it doesn't matter how many times you flipped it. The probability of the next time that you flip this coin is always going to be 1/2. So like, let's see, how do I complete this thought? This column, like either you have a coin that is heads or a coin that is tails. And what the element shows is the probability of the next, of starting from heads and going to heads, or starting from heads and going to tails. So let's see. Let's try to draw this out a little bit more. Like maybe you start a coin that has heads. You can either get heads or you can get tails. I'm basically just going to be drawing the same graph that I had before, but heads, tails, heads, tails, heads, tails, all the time, forever. Let's see. So we get this little graph, this nice little graph, and what that spot means is we are currently at any space that is heads, and then we move to the next heads space. So what I'm trying to say is that the elements of the matrix are these arrows, more so than the nodes. Like, if I understand correctly, and somebody please correct me, I am literally a hobbyist. I don't remember any of this. I'm making it up as I go. I think that all of the elements of a matrix are the transition arrows, like the movement from this space to this space. And so then the second one here, I said that the row was heads and the first row was heads, the second row was tails. This one then represents this state transition. You have a coin that's heads and then you flip tails. The probability of that is 1/2 as well. So what I wanted to show is that if it is true that multiplying two Markov matrices represents, it can track probabilities along the way, is what I'm trying to get to. Like, it can, it should be able to represent the probability of being in one of these many different parallel universes. And what's cool is that if those probabilities are always the same, what we can do is we can plug this into a giant calculator, and this matrix, we just need to basically press the exponent button. We can type this thing into our calculator and then press the exponent button, and then and we'll know what the probabilities are of which of these many different parallel universes. So imagine that this isn't just 2, but it's 200 or something, like flipping coins 200 times in a row. Well, if it's a fair coin, it doesn't matter. We can keep flipping, and it's always going to be 1/2 for the next one. So what the hell are you talking about, John? Hurry up. Let's get to it. Let's see what happens, though. Let's verify that for ourselves. What happens when we multiply the row 1/2, 1/2 with the column 1/2, 1/2? Remember, we're going to take the first number of each and multiply them. So 1/2 and 1/2 multiply to 1/4. And then we take the second number of each and we multiply them. And then we add those together, and voila, 1/4 and 1/4 add to 1/2. And then similarly, all of these entries, they're all the same. They're all going to turn out to be 1/2. So what I claimed is true if it were a fair coin. If you flip a fair coin 200 times in a row, you're still going to keep getting 1/2 for the next probability. But what if we adjusted those numbers just ever so slightly? If we adjust those numbers ever so slightly, this is a really powerful way to track how much we've drifted away from the expected, or away from the original probability. Like, it's a way to calculate probability in a super neat, clean way. I don't know where I'm going with this. Let's just get some matrix multiplication practice. 0.52, 0.49 multiplied by 0.52, 0.48. All right, 0.52 times 0.49 plus 0.48 times 0.51. I haven't run this yet. What does this turn out to be? 0.52 times 0.49 plus 0.48 times 0.51. Let's ask ChatGPT, and 0.485. Wait, something went off. Oh, I got this wrong. I think 0.5249 and what am I talking? Okay, we got to practice our matrix multiplication, y'all. We're doing this live, so practice. All right, this is actually going to be 0.52 times 0.52 plus 0.49 times 0.48. Okay, so the first number in the first row, which is 0.52, and then the first number in the first column, which is also 0.52. And then the second number, the second number in the first row. Okay, I have to take a break, unfortunately. I'm so annoyed. Okay, be right back. Okay, y'all, what's going on? So, yeah, we've got some maintenance happening. So, this is just a good opportunity for a short break and hang out and chat. If anybody out there just wants to hang out and chat for a second, or I could continue. Yeah, let's just try to continue. But I know we're going to get interrupted again in just a second here. Oh well. So where are we? So we've got this matrix, and we are multiplying those numbers together. And this time I wrote it down correctly. The second number in the first row, which is 49, times the second number in the first column, which is 0.48. And then this time, let's get it, 52, let's ask ChatGPT, 49 times 0.48, 5056. So, 0.5056. So I'm going to round that to 0.506. And then let's verify that the columns should still continue adding up to 1. Is that true? I think that's true. So verify for yourself that this next element is going to be 48 times 0.52 and 0.51 times 0.48. Nope. Okay. Maybe it doesn't continue to add to 1, but in the original state it is adding to 1. Let me double check. 0.48 times 0.52 plus 0.51 times 0.48. Yeah, okay, cool. All right, so it is not true, and now I will remember that better because I made that mistake live on YouTube. Where did it go? Why is this not working anymore? Oh no, maybe it does. Yeah. 0.4944. Okay, so it does. Whew, that's what I thought. So those two add together to 1. And what's happening here, like, why are the numbers ever so slightly different? And it is because coins are ever so slightly heavier on one side, and they're also more likely to land on the side that you started with. Like, it's very difficult to find a perfectly balanced, fair coin in the real world. There's always just like a tiny little difference, like 52% chances as opposed to 51% chances or 49%. But if you flip a unfair coin like this many times, you'll see that the probability of being in one of those specific parallel universes is going to be much higher, I think, from what I remember. I have barely refreshed any understanding of this, and this is almost the extent of my knowledge of Markov chains. I know that they're very useful for calculating the chances of something happening if probabilities are ever so slightly different and projecting into the future. So, Prisoner's Dilemma and Markov chains. What's a real-world example of that? Alice and Bob. Alice and Bob. We're back to Alice and Bob. This time they're no longer prisoners. Instead, they both work at a FAANG company. They both work at a company like Google or another one, Meta, maybe. Pick your company of choice. And in the prisoner's dilemma, it's very important that people are not loyal to each other. There's no loyalty between Alice and Bob, and they can defect and choose to screw over the other player equally. Maybe in this scenario, maybe if we're taking the metaphor, infinite happiness is a promotion, and a little bit of sadness is extra work for the other person. If you screw over your teammate, you're more likely to get infinite happiness with a promotion. And yeah, so the choice, if everybody cooperates, there's just like a little bit of work for both players in the game. If everybody does their work correctly, everybody has to do a little bit of work. If one person screws over the other, they get promoted and the other person does all their work. So that is super similar. You can take this idea of a Markov chain and you can run the numbers. If you have multiple people coordinating across multiple different teams, and there's not just two people, but there's many different columns and rows. N is basically the number of employees at a company, or the number of teammates working on a shared project that is working across teams. Maybe you have a lot of loyalty to your immediate teammates, you love them. But if you're working with another team on the same project and you're incentivized to not do your part of the job because you're waiting for somebody else to complete their part of the work, that's kind of like defecting, like procrastinating your part to try to maximize, like put your energy into another project that is more likely to get you promoted or something. I'm not going to try to make up numbers here, but I remember seeing a very funny, very hilarious, sardonic slide deck about this at Google while I worked there. It was something like an initial matrix with like 99% or 99.9% or something chances that that everybody does their job correctly, and there's just like a 1% chance that somebody defects and is sloppy. And it's just hilarious. It was so funny. I wish I could relay it. I wish I remembered or wrote down something about it. So any Googlers out there, please feel free to relay that info. I don't know if it's public, but it was like called the slime problem, I think. And I just remember it had Markov matrices, and I was like, I briefly remember that. That's awesome. And it got really complicated. It got really thorough, and like the math started getting really advanced. And I was like, I do not have time for this. I got to get back to my work and get back to my project. So now I wish that I read the slime problem slide deck a little bit more carefully so I could relay it to you all, but I didn't. Anyways, there's a fun little story. Also, yes, this gets way worse as the number of employees goes up. And that has been my personal experience for sure. Cool. What else? Why am I talking about all this? I said that we'd do something about ChatGPT. 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 All right, so Markov matrices. I remember when I was a TA for a linear algebra class, I didn't learn this in mine, but I learned it in while I was a TA for another. It was so cool. I remember seeing that they can be used to build like a really neat, really naive autocorrect system. Be right back. I gotta be right back again. All right. All right, y'all, we're back. We're back. So we're talking ChatGPT now. I see that we have a couple concurrent viewers. Hello, welcome. My name is John. I'm a math hobbyist. I'm trying to review all the math that I learned way back in the day and try to get good and just try to study math as a hobby because I love it. I just love it. I think it's fun. So I remember that you can use Markov matrices to build like a really simple autocorrect system. And like based on the prior word, the probability that the next word is going to be something else. I learned this like around 2010 or something, and the iPhone was relatively new. I don't remember when, but they had just improved autocorrect in the keyboard, like really made some improvements. So I was like, oh, that's so cool. That's very timely and relevant to me because I love the iPhone. And so, yeah, Markov matrices can be used to build like a really cool, simple, naive autocorrect. Like maybe it's, you calculate the percent probabilities that if you have the word the, there's a lot of possible next words. What is the phrase? I don't know. Quick. The quick brown fox jumps over the lazy dog. You can calculate the probability, and maybe you have like a humongous table of, given the word the, what is the percentage, how many times in all these Reddit articles that we've scraped, that we've downloaded from the internet, how many times is the following word quick following the word the? I don't know, maybe it's 1%, maybe it's less, I have no idea. Probably less than 1%. And then if we've gone this way and if we've gone that direction, then what's the probability that the next word is brown? I don't know if Markov chains capture in any way like increasing the weight here on this arrow. So I would love if somebody technical who understands what the hell I'm pulling out of my ass knows. I don't think so. I think that this is just every time that the word quick appears in Reddit articles, the following word is brown. In the total, just like a simple calculation of that, maybe that's like 0.01%, like some small amount. But yeah, like you can model iPhone autocorrect systems as a Markov matrix. And I thought that was super cool. And I just thought that that's somewhat timely because people say that ChatGPT is a fancy autocorrect. That is a trite saying that a lot of people say. ChatGPT is a fancy autocorrect, and then it is a fact that I know that that it uses linear algebra heavily. I've also heard the term huge, inscrutable matrices. Huge, inscrutable matrices. I think that is how big these graphs are. It's not just the dictionary of all English words, but every single possible combination of, it's not just English, it's not just English and every other language. It's actually more, from what I understand, it is more about individual tokens. So maybe the word the is the what's the word, phoneme or something, like the sound th and then right? Maybe the word the is two separate individual pieces that makes the word the. Is another good one. That you're going to hear a lot of ums in this stream because I'm too lazy, and I'm too lazy to go back and edit these videos. Sorry, not sorry. I've got better things to do. I hope you enjoy it nonetheless. This is live because I'm trying to practice. So the probability of saying so after is pretty high. So this is a humongous table where each of these state changes, each of these transition diagrams, these arrows, is an entry in a huge, inscrutable matrix. I don't know. That's my mental model for these two together, but I don't think that's accurate. In truth, ChatGPT is a little bit it's quite a bit more sophisticated than just a Markov matrix. But you could build a really terrible, really simple ChatGPT for yourself using nothing other than the matrix multiplication that we created today. Because I know that because I think I built one of those, or I at least graded some homework of other people who built one. And it was just like the iPhone autocorrect, like following this word, you click this word, then you click this word. And then you can build those hilarious sentences where like you just keep pressing the first suggestion again and again and again. Yeah, so I hope that was some fun flavor for today. I think that one could probably also make an interesting discussion around ChatGPT and Pascal's wager, but maybe we'll save that for another day. All right. Let's move on. All right. Before we solve a couple of problems, here I did want to follow up and get the formal definition of a vector space according to a few different people. Let's see, we've got a few views, a couple of viewers. Please leave any questions. And if anybody sees this video after the fact and you're enjoying it, I very much appreciate feedback. If you have any questions about any topic in particular, please leave a question in the comment section. If you have any corrections, please correct me, because I'm probably very wrong on a lot of this stuff. Or if you want to expand on any of these weird metaphors that I'm coming up with on the fly, please do. I think it'd be really cool to build a cool community here of math geeks and hobbyists, recreational math people. So, yeah, there's a little shout out, like and subscribe, all that normal stuff, all that good stuff. Formal definition of a vector space according to ... I see this kind of like the explaining a thing to different levels. Like there's those videos on YouTube, like a musician explains the same concept to a kindergartner and a high school kid and a university student and a graduate student and a professional and a master. Usually there's 5, right? So I wanted to show how different they are across these different books that we're working on. I didn't get around to writing down Shilov's because I don't have time for that, apparently. But here's Strang's. The requirement: all linear combinations CV plus DW must stay in the vector space. The row space of A is spanned by the rows of A. The columns of A span C of A. Matrices M1 to Mn and functions F1 to Fn span matrix spaces and function spaces. Okay. I need to open that again. I'm starting to think that I wrote down the wrong thing, but I think that was his definition of a vector space. But it is, like, he wrote down these, he has these rules, and it is, a vector space is all combinations of vectors. And the rule is that in the vector space, every linear combination, when you add 2 vectors, they must also be another vector. If you multiply a vector by a scalar, then it should also be a vector. So in particular, like CV plus 0W, like if you don't have any W and you just multiply the vector V by a scalar, a number C, then it must stay in the vector space, which means CV should be a vector as well. So some other books will call that closure of multiplication, or closure of addition. So that's interesting. I mean, for me, that leaves more questions than answers, but I did just jump right to it. I skipped several sections and just skimmed the book and got that. So, that's my fault. Here is Axler's definition of a vector space. 1.19, definition, addition and scalar multiplication. An addition on a set V is a function that assigns an element u plus v in V to each pair of elements uv. So that is for each, that's written just like a little bit weirdly backwards to me, but it is like anytime you have two things, whatever they are, two things, you can create another thing. If you have two things, you can create another thing. It's still considered a thing in your vector space. So a scalar multiplication, I ran out of time yesterday and I missed this. So a scalar multiplication is a super similar definition, but it is like, he's going to say something like that it assigns for A being a number and V being a vector. I wish I had a physical book so I could quickly find out. I don't think that he uses a field F. I think what he means by F throughout Axler's book is you can either think of that as the real numbers or the complex numbers. But in general, yeah, he just uses the letter F to mean either one of these. You can think of either one of these throughout the entire book. I believe he doesn't give a more abstract definition of field. But I'm going to just repeat my simple explanation. In the real numbers and the complex numbers, you can add numbers, subtract numbers, multiply numbers, and divide numbers. There are other things called rings, for example, which do not have division, but they do have the other things. And then there are even more weird spaces called groups, where you maybe don't have multiplication. You only have addition and subtraction. That's pretty hand-wavy. This whole stream we could call hand-wavy, and that's okay. That's a good thing. Back to what we were just doing, we were just saying that these are two rules. He doesn't use the word rules. He says these two things. The definition of addition is the fact that if you have u and you have v, then you can combine them and you can point to, hey, we have another one in this party, in this vector space. There's another guy in here that's a combination of those two. Cool. 1.20, definition of a vector space now. A vector space is a set V along with an addition on V. So this last one was defining what is addition on V, and a scalar multiplication on V. We just defined both of those, such that the following properties hold. So we need to have these rules. A vector space has to have this familiar rule that we're pretty used to and we assume is always the case. When you add two numbers, you can add the first one and then the second one, or you can add the second one, then the first one. Whatever. 1 plus 2 equals 3, and 3 also equals 2 plus 1, right? We can swap the order. 1 plus 2 equals 2 plus 1. This is the same idea. It's just commutativity, flipping addition. Associativity is Well, we can first add these and then add the third. We can first add the first two, then add the third, or we can first add 2 and 3 and then add 1. Like in our familiar numbers, we can add 1 and 2 and then add 3, and that is the same thing as 1 plus 2 plus 3. So that's pretty familiar. That's like a very similar structure thing. We're used to this in numbers, but it's interesting. I mean, it's kind of formalism, but it's, if we have 3 different vectors that we can add these in different orders, not always, there's not a specific order that you have to add them in. They're all going to equal something like this. We have an additive identity. Okay, that's interesting. There exists something that we call 0, such that anytime that we add 0 to any vector, I must have written that down wrong. That should definitely be 0 plus v equals v. You can add 0 to any number and you get the same number. You can add a 0 vector to any vector and you get the same dang vector. So the 0 vector is just 0, 0, and you can add that to anything AB and you still get AB, as one example. I showed in a previous video that I gave like a brief hobbyist hand-wavy definition, but it was closer to Axler's definition than Strang's, I think. But I showed in a previous one that you can think of something like x squared plus 1, that this can be considered a vector space. Maybe we denote it as like polynomials of degree 2 or something like that. And that's because so far we have these sorts of rules. X squared plus 1 plus, I don't know, x squared minus 3, just making up random stuff, that is 2x squared minus 2. We still have a polynomial that's of degree 2 or less. I have to cheat a little bit there. That is still a second degree polynomial. But it is important that 0 is still a polynomial. We consider that a second degree polynomial, even though there are no x's. And that follows Axler's rule that we just came up with. This is the same dang thing. This is called an additive identity. In this case, if polynomials, we can add, no matter what, if we have ax squared plus bx plus c, is there something, what should I denote this as? Is there some other thing that we can add to that so that it still is ax squared, so that it doesn't change the original object? Ax squared plus bx plus c. Is there anything? Well, yeah. When p of x is literally just the number 0, that works. You can add 0 to any polynomial and you still get the same dang polynomial. All right, so we sort of understand additive identities and additive inverse. Next rule. For here I started cheating and using this fancy notation that I wish I went back and fixed. But for every for every vector, there exists another vector such that when you add the two, they equal this abstract thing that we claimed always exists, the additive identity. So what do you mean that there's always some other thing? Maybe if our first polynomial p of x is x squared plus 1, what can we add to that so that it equals 0? Well, we can add negative x squared minus 1. When you add those two together, p plus q equals 0. So that's kind of interesting, I think. All of this is pretty familiar, pretty interesting, pretty familiar. Multiplicative identity, there should be something 1. And again, I had run out of time, so oh well. Here's my quick, brief sketch of what Axler's book says. There has to be something that anytime you multiply it by 1, like, oh wait, sorry. Blah, blah. One more time. There needs to be a number 1, which is in your field, so that you can multiply any vector by it, whatever this 1 is. Because remember that we're no longer talking about specifically real numbers or complex numbers or polynomials or other things. The idea of a vector space can extend beyond that to more abstract, weird other worlds that math can understand and study. So polynomials is one case. Like Axler's book, for example, only talks about R or C, but something that's even simpler are fractions. The fractions, like 1/2, like 5/12, whatever, that is also another case of a field, and it's interesting that no matter how many times you add fractions, like rational numbers, you're always going to get another rational number. So in all of these cases, these are familiar, regular-ass numbers that all have the same 1 that we're used to. So it's kind of hard for me right now to remember an example that's like more weird, but we can come up with weird ones next time or in a month or something. I don't know when. But there should be a 1 that you can multiply by, and you always get the same vector back. And we need to have distributive property. When you multiply by an element, like when you add two vectors together and then you multiply by a number, that it should be the same thing as multiplying the first vector by that number and then adding the second vector multiplied by the number. So that's distributive properties that we're used to. Like very similar to the regular numbers, to the real numbers or the fractions and others. Cool. I would ask any questions, but I don't think we have any viewers at the moment. So next, I wanted to show just for fun, what does this guy define a vector space as? It would be nice if I had time to show Shilov, because I think it would be similar to this, but just like way more terse. But it would be as formal, I think, as this. Strang's is like pretty informal, like it's pretty metaphorical almost, and it like you need to define like what is a row space, what do you mean quote unquote spanned. I mean, I really like Strang's book so far. I really love the exercises. but that definition threw me for a loop a little bit when I read it. I might have been reading the wrong part. I don't know. Anyways, here's Lang. She love is red. Red is hard. Red is the color of blood. Healthy coursing blood through one's body. Lang is a color of dried blood, if you ask me. This book is brutal. It's beautiful. It's absolutely beautiful, but it is brutal. This is a scary book. So many of my videos have been talking about scary books. And so the point for anybody who's afraid of math is at any level, because this stream I'm trying to go from basic level to scary level. At some point, I think that the math in this video is scaring somebody. Like if you're a viewer and you're watching this, at some point, this probably is scaring you. This scares me a little bit. Sort of, not really. Although I do hope that we can get some experts in the chat so that they can write down what scares them. I want to know what scares experts. Because I know that to experts, like this is child's play. This is child's play. They teach this stuff. I suppose you need to know this one. You need to get through this bad boy before you get to this really scary one. So let's finish this dang stream. It's taking too long. Lang, I'm just going to read it out loud just for fun. A module over a field is called a vector space. That's on page 139, period. A module over a field is called a vector space. All right, so I did talk about fields, so good for me. But what the heck is a module? The other books do not talk about what a module is. All right. So what is the definition of a module? First, let A be a ring. What the heck is a ring? So let's move on. Whatever a ring is, a left module over A. What do you mean left? What? Left module, all right, over A, or a left A module, M, is an abelian group, usually written additively, together with an operation of A on M, viewing A as a multiplicative monoid by R12, Ri2. What? So I do know what a lot of these words mean, but I would have to double check myself on monoid, for example, such that for all A, B in A and XY in M, we have this. So hey, okay, like this is sort of familiar. We are getting distributive property. This is actually super similar. So that is like a core idea in what a vector space is. You need to have this multiplication by a number that can distribute through so that you can add numbers before or after, or you can multiply by the number after adding the vectors or things, even though this isn't a more abstract thing called a module. But in a similar way, one defines a right A module. We shall deal only with left modules. What does that mean? Like save right A modules? Or save right modules for another book? Like for the sequel of this book? Like we only have time for left modules, unless otherwise specified, and hence call these simply A modules, or even modules if the reference is clear. If you're a dummy, if you're following along and you can understand what I'm talking about, if the reference is clear, we're gonna just abbreviate this to modules. Well, that's what he does over here. He does not talk about a ring at all. Just out of nowhere, he's like, a module. Like, by now, you should get it. You should get this by now. A module is over a field, or over a ring. It doesn't matter what the ring is over here. Anyways, so if we wanted to do this exercise, I skipped this one. Let A be a ring. What is a ring? Okay, let's flip back, and I don't know what page that is on, but it would be something like a ring is a group, and then you would go, what the hell is a group? And then that's on, I don't know, probably page 1, to be honest. But my point here is saying there's this beautiful hierarchy. I'm trying to get to something positive here. I'm not saying this to say that this is scary and horrible or anything like that. It's actually really beautiful. It's really, really beautiful math. Even like the undergrad abstract algebra book I have has this exact same thing. You've got groups, you've got rings, you've got modules, and then you have like a vector space. Like, and each of these like is a more specific version of the prior thing. I should have written this in a more friendly, maybe in red, lifeblood red. This is nice. This is actually really beautiful. This is, in a sense, one of the goals of abstract algebra, is understanding these increasingly weirder and different worlds that are less and less familiar. And I just think that they're super cool. Abstract algebra. In a future series, I suppose, we'll start working through an abstract algebra book or two, and we'll probably be trying to work some problems from Lang and struggling with it. Cool. So I totally flubbed this yesterday because my iPad was no longer showing on screen, so I wanted to do it again. And now let's move on. All right. So I said we'd work a couple of Strang problems. They're very easy. They're going to be very, very quick. So let's figure out what were they. 1, 2, 1, 1, 3, 4. Strang. 1, 2, 1. I feel like we can probably do this on like 2 little things. Strang. 1, 3, 4. And we can do them together. Hey, thanks for the likes, everybody. I see that we got a few likes. I appreciate it. Thanks, y'all. I put the chat, I slowed down the chat because I wanted to focus this time, but I'll let chat free next time, maybe. So I apologize. You have to wait 10 minutes. That's a long ass time to chat, I know. To sit through a bunch of boring math. But that's okay. It's worth it. Problem set 1.2 in Strang. Calculate the dot products U dot V and U dot W. And, okay, there's more sub-problems than I thought. U dot V plus W. Okay, this is a little bit longer. I thought it was just calculate one dot product. And I was like, okay, that's so easy. I can do that. All right, well, we'll get through all these. This is still one of the easy problems. Negative 0.6, 0.8, 4.3. And W is 1, 2. Okay, so I cheated and I just said multiply the first number of this one with the first number of this one. That is formally called the dot product. So I'm just going to work it and you'll see what I'm doing, I think. U dot V is negative 0.6 times 4 plus 0.8 times 3. And we can ask ChatGPT. Negative 0.6 times 4 plus 0.8 times 3. 0.8 times 3. Oh, I should have seen it. Yeah, that is 0. Okay. I shouldn't laugh. There's no reason that I should have noticed that. I saw decimals and my brain immediately was like, we need a calculator. But yeah, 6 times 4 is 24, and so is 8 times 3. So we could have seen it, but that's fine. U dot product with V plus W. So we're getting like a lot of really good little matrix and vector. I want to write it horizontally. We're getting like a lot of nice little calculation problems. These are nice. V plus W is 5, 5. So the dot product of those two is going to be -3 plus 0.8 times 5 is 4. And that is 1. All right, so done. Oh, wait. Oh, I skipped ahead to this one. U dot W. Whatever. U dot W. Hey, this is a brighter color. Let's use this. U dot W is going to be -0.6 plus 0.8 times 2, which is 1.6, which is 1.0. U dot W, check. And now finally W dot V. W dot V is going to be 1 from the W. Well, let's just write it again here for clarity. 12.43. We multiply the first number of each together, and we multiply the second number of each together, and then we add those together. So that's 10. All right, voila, I think we're done with that one. Now, in section 3, my paper version is still in the mail, so you know what, I apologize. We've got the pirated version at the moment. Section 3, problem 4 says, multiply AX and BY and IZ. Why the hell are you using I instead of C? Like, is it CZ? Like, does he not like the sound of C? Or, like, that's so strange to, like, I is ICY. Okay, never mind. I'm a dummy. It makes sense. Using dot products as in rows of A dot X. Okay, so first we have AX equals 212,424,010 multiplied by this skinny, tiny little matrix 1, 2, 5. So I said it that way because, hey, this is also a matrix. It's just a 3 by 1 matrix. Three rows and 1 column instead of a square one. So matrices can be different sizes. They don't always have to be square. All right, so we're getting some practice in. Let's just say it out loud. 2, 2, 10. Add those together, it's 14. This is good mental math practice, y'all. 4, 4, 20 is 28. 0, 2, 0 is 2. Cool. Now, bx is going to be, not by for whatever reason, is 1, 0, 0, 1, 1, 0. These are cool examples that he's choosing. This is called like a lower triangular matrix because of the ones create a triangle, which is neat. Doesn't matter. He'll teach more about that later in a future section. All right, so pronouncing them out loud. 400, 440, 4410. All right, there's 4818. And C. Now our final matrix calculation that we're going to do is this really special, delightful, lovely matrix. It's beautiful. 1, 0, 0, 0, 1, 0, 0, 0, 1. Times something. Oh my gosh, this could be, what do you mean Z? I'm used to multiplying numbers, not letters. All right, just pronouncing out loud. Z1, 0, 0. Just a reminder, anybody still following along or who might have gotten lost, we are multiplying each of these rows with the one column. And I'm taking one element from one and multiplying it by like the first number of each, multiplying the second number of each, and then the third number of each, and then adding all of that together. So now we have Z1 for the second row, for the second item, 0, Z2, 0. Third item, 0, 0, Z3. Hey, this thing didn't change this thing. These two are still equal. So, IZ still equals Z. Remember those scarier books? In this case, I is the number 1 in the set of matrices. I don't know if that's the right notation, but it is the number, quote unquote, 1. It's the identity matrix. That's cool. I wasn't planning for that, but there's a great example for an identity, like the number, quote unquote, 1. Yeah, like it didn't, you multiply by that thing and it didn't change the vector. Cool. I think that's everything I wanted to do today, so I think we'll be done unless there are any questions. Hey, Jeffrey, good to see you, dude. Thanks for the emojis. Did you see my guitar drama video, Jeffrey? I'd love to get your feedback on that. I hope I handled it professionally, let's say. Also, any feedback about all this math lecturing, like, this is really fun for me. It's a really fun hobby to start picking up. I'm being somewhat snarky here and there, but I genuinely really love all this stuff. And it's really fun for me to try to be vulnerable and make mistakes on the internet, including in something that I have ever so slightly more of an ego in, like mathematics, as opposed to classical guitar, where I have zero ego. I'll check it out. Yeah, it's a doozy. All right, that's it. you'll probably get the gestalt of it in the first 10 minutes. I don't know if you need to watch the entire hour-long video, but you could watch it at 2x if you want to. It's just me ranting to the camera. Thanks everybody for watching. My name is John. I'm the math hobbyist, and this is super fun for me. Like and subscribe, the math hobbyist. Like and subscribe. I'm available for tutoring. I can be your one-on-one tutor. I can be your kid's one-on-one tutor. First student, I'm pretty rusty. I've tutored a lot of people in the past, but nowadays I don't have a private student. For the first student, I'm going to be pretty dang cheap. So let's say the first student in each subject, like linear algebra or calculus or number theory. First student in each subject, I'm going to be pretty cheap. Following students, I'm going to be fairly expensive, I think. So get it while it's hot. First student, let's do this. I would love to teach more people privately again. So not pretty dang expensive is an exaggeration. But it's not going to be as cheap as a first student. Thanks for watching. Like and subscribe. Bye.